A segment tree is a data structure commonly used to efficiently perform range queries, such as sum, min, and max, and updates on an array. The basic idea is to divide the array into smaller segments and build a binary tree structure to represent these segments. Each node in the tree represents a segment of the array, and the root node represents the entire array. The leaves of the tree represent individual elements of the array. To construct a segment tree, we start with the original array and recursively divide it into halves until we reach the individual elements. Each node in the tree contains information about the segment it represents, the starting and ending indices, and additional data based on the specific problem we are solving. In this video, we store the sum of the elements within the segment represented by a node. For the array 1, 3, 5, 7, 9, 11, first, we have segment 0 to 5 as the root node, the whole array. Split segment 0 to 5 into 0 to 2 and 3 to 5. Split segment 0 to 2 into 0 to 1 and 2. Split segment 0 to 1 into 0 with value 1 and 1 with value 3. Combining segments 0 and 1, we have the value of segment 0 to 1 as 4. The value of segment 2 is 5. Combining segments 0 to 1 and 2, we have the value of segment 0 to 2 as 9. We do the same steps for the right segment 3 to 5. Keep splitting until we reach the individual elements, then count up the tree. We ended up having segment 3 to 5 with value 27. Finally, by combining segments 0 to 2 and 3 to 5, we have the root node with value 36, the sum of the entire array. The construction process typically takes n time, where n is the number of elements in the array. For an update, we start at the root node and recursively traverse down the tree until we reach the leaf node corresponding to the updated element. We update the value stored at that leaf node and propagate the changes up the tree, updating the values of parent nodes accordingly. For example, we want to update the value of element at position 3 from 7 to 8. From the root, we go right to reach segment 3 to 5. Go left to reach segment 3 to 4. Lastly, go left to reach leaf node 3 and update its value into 8. Then we propagate the changes up in the tree. Update the value of segment 3 to 4 into 17. Update the value of segment 3 to 5 into 28. Then finally, update the value of the root node into 37. For a query, we start at the root node and recursively traverse down the tree based on the query range. At each node, we check if the node's range overlaps with the query range. If there is no overlap, we return 0. If there is a complete overlap, we return the value stored at that node. If there is a partial overlap, we recursively visit the left and right child nodes to get the results and combine them. For example, we want to query the sum of the range 1 to 4. Start from the root segment 0 to 5, there is partial overlap, so continue to query in the left and the right. For segment 0 to 2, there is partial overlap, continue to query in the left and the right. For segment 0 to 1, there is partial overlap, continue to query in the left and the right. For segment 0, there is no overlap, then the result is 0. For segment 1, there is a complete overlap, then the result is the node's value 3. Combining segment 0 and segment 1, we have the query's result for segment 0 to 1 is 3. For segment 2, there is a complete overlap, then the result is the node's value 5. By combining segment 0 to 1 and segment 2, we have the query's result for segment 0 to 2 is 8. For segment 3 to 5, there is partial overlap, continue to query in the left and the right. For segment 3 to 4, there is a complete overlap, then the result is the node's value 16. For segment 5, there is no overlap, then the result is 0. By combining segment 3 to 4 and segment 5, we have the query's result for segment 3 to 5 is 16. Finally, by combining segment 0 to 2 and segment 3 to 5, we have the query's result for the entire array is 24. The time complexity for both queries and updates is O log n, where n is the number of elements in the array. Overall, segment trees provide an efficient way to perform range queries and updates on arrays, making them a useful data structure for various algorithmic problems. It can be extended to solve a wide range of problems, including finding the minimum or maximum element in a range, computing the sum or product of elements in a range, finding the greatest common divisor, GCD, or least common multiple, LCM, of elements in a range, and many others.